The universe has had 13 billion years to produce intelligent life. It has not produced a single confirmed signal. Those are not the words of a philosopher. That is the conclusion reached by Enrico Fermi, one of the most rigorous physicists of the 20th century, over lunch at Los Alamos National Laboratory in the summer of 1950. For decades, we had assumed the galaxy must be teeming with civilizations. The numbers demanded it. Hundreds of billions of stars, tens of billions of potentially habitable worlds, and a universe old enough for life to have emerged, evolved, and colonized entire star systems millions of times over. Then Fermi did something no one at that table expected. He set down his fork, he looked up, and he asked a question that shattered the assumption entirely. And 75 years later, not a single scientist on Earth has been able to answer it. The question was 3 words. But where is everybody? It was not rhetorical. It was not a joke. It was the product of a mind that could not stop calculating, even between courses at lunch. Fermi had done the arithmetic in his head. A rough, fast estimate, what his colleagues would later call a Fermi estimation, using the number of stars in the Milky Way, the fraction likely to have planets, the fraction of those planets capable of supporting life, and the time it would take for even a single civilization to develop interstellar travel. He ran the numbers against the age of the galaxy. He accounted for the speed of light. He considered colonization timescales. And the result was not ambiguous. The numbers did not merely suggest that we should have heard from someone by now. They demanded it. The galaxy should be saturated with evidence of intelligence. It should be obvious, unmissable. Our galaxy alone contains somewhere between 200 and 400 billion stars. Over the past 2 decades, data from NASA's Kepler Space Telescope and the Transiting Exoplanet Survey Satellite, TESS, has confirmed that most of those stars have planets. A conservative estimate published in the Astrophysical Journal in 2020 puts the number of potentially habitable worlds in the Milky Way at roughly 40 billion. "40 billion chances in one galaxy. And our galaxy is just one of approximately 2 trillion galaxies in the observable universe." The radio astronomer Frank Drake attempted to formalize this logic in 1961 with what became known as the Drake equation. He broke the question into 7 pieces: the rate of star formation, the fraction of stars with planets, the fraction with habitable conditions, the fraction where life actually emerges, the fraction where intelligence develops, the fraction that creates detectable technology, and how long those civilizations survive before going silent. He did not write it to produce an answer. He wrote it to organize a conversation. In November of 1961, Drake gathered a dozen scientists, among them a young Carl Sagan, at the Green Bank Observatory to settle a single question: whether the search for other civilizations was a serious scientific pursuit or a waste of a telescope. The equation was his agenda for that meeting, scrawled to give the discussion a shape. It was never meant to be solved. It was meant to show exactly where our ignorance lived. The result was not a number. It was a range so vast it told us almost nothing specific and everything important. Even with the most pessimistic assumptions, the expected number of detectable civilizations in our galaxy was greater than 0. 6 of the 7 terms have, in the decades since, slowly come into focus. We now know stars form readily. We now know planets are common. We now know habitable zones are not rare. But the final term, how long a technological civilization survives once it learns to broadcast, remains entirely unconstrained. It could be millions of years. It could be a few centuries. Everything hinges on a number we have exactly one example of. And that example is still running. And yet, as Fermi observed, the number we have actually found is exactly that: 0. No signals, no probes, no megastructures, no waste heat, no anomalies in the infrared that would betray the presence of a civilization harnessing the energy output of its star. No evidence of any kind that anyone else has ever been out there. Consider what even a moderately advanced civilization could accomplish with a head start of 1 billion years. Our own species has gone from the first controlled flight to interplanetary probes in barely a century. A civilization with a billion-year advantage, even expanding at a fraction of the speed of light, could have colonized the entire Milky Way several times over. We should be swimming in their artifacts. We should be tripping over their infrastructure. In 1964, the Soviet astronomer Nikolai Kardashev proposed a way to rank such civilizations, not by their politics or their biology, which we cannot begin to guess at, but by the one thing any expanding intelligence must consume: energy. A Type 1 civilization harnesses all the energy available on its home planet. A Type 2 captures the entire output of its star. A Type 3 commands the power of an entire galaxy. We do not yet qualify even as Type 1. Humanity sits at roughly 7/10 of that first rung. But the scale matters because of what it implies about visibility. A Type 2 civilization, by definition, would have to do something with its star's energy. And whatever it built to capture that output, a swarm of collectors, a shell, what the physicist Dyson imagined as a sphere enclosing the sun itself, would swallow visible light and re-radiate it as waste heat in the infrared. It would leave a fingerprint. A star that glows wrong. We have looked for that fingerprint. In 2015, astronomers combed infrared data from 100,000 galaxies, hunting for the telltale heat of a civilization that had spread across billions of stars. They found nothing unambiguous. Not one galaxy out of 100,000 showed the glow of an intelligence grown large enough to fill it. There was one moment, though, when we thought we might have found it. In 2015, a star catalogued as KIC 8462852, later nicknamed Tabby's star after the astronomer who studied it, began behaving in a way no one could explain. Data from the Kepler telescope showed its light dipping by as much as 22% at irregular intervals in a pattern no planet could produce. A planet the size of Jupiter blocks barely 1%. For a brief, electric period, serious astronomers entertained the possibility that we were watching something being built around that star. A vast, unfinished structure, a Dyson swarm in progress. The world's largest radio telescopes turned to listen. They heard nothing. Later observations pointed, most likely, to an uneven cloud of dust. Most likely. The star has never been fully explained either. And there is a far cheaper way to fill a galaxy than to cross it yourself. A single self-replicating probe, a machine that arrives at a star, mines raw material, builds copies of itself and sends them onward, could reach every system in the Milky Way in a few million years. A few million years against a galaxy more than 10 billion years old. The mathematics is not subtle. If even one civilization, anywhere, across all of that time, had ever launched one such machine, its descendants should already be here, in this solar system, in orbit around this planet. The galaxy should not be quiet. It should be deafening. That is the Fermi Paradox. Not just the observation that we have not been contacted, but that the universe appears, from every instrument we have pointed at it, across every wavelength we have searched, completely, thoroughly, impossibly quiet. The first serious attempt to listen was made in 1960 by a young radio astronomer at the National Radio Astronomy Observatory in Green Bank, West Virginia. Frank Drake pointed a 25-meter dish at two nearby sun-like stars, Tau Ceti and Epsilon Eridani, and listened for 80 hours. He called the effort Project Ozma, after the princess of a land far away and difficult to reach. He heard nothing that could not be explained by natural phenomena. There was a question in those early years of where to even point the receiver. Which frequency, out of the billions available, an alien transmitter might choose. Drake and his colleagues settled on a stretch of spectrum near 1,420 megahertz, the frequency at which neutral hydrogen, the most abundant element in the universe, naturally emits. The reasoning was almost poetic. Any civilization doing radio astronomy would know that frequency. It is written into the physics of the cosmos itself. They called the band the waterhole, the place where, like animals gathering at a watering hole on the savannah, different species might meet in the quiet. We have been listening at the waterhole for 60 years. Nothing has ever come to drink. But Drake was not discouraged. He had always understood that the search would take time. What he started that year would grow into a global effort spanning 6 decades, involving telescopes on every continent and, eventually, the largest radio telescope ever built, The 500-meter aperture spherical telescope, completed in 2016 in Guizhou Province, China, is the most sensitive listening device humanity has ever constructed. Its collecting area is roughly the size of 30 football fields. SETI, the search for extraterrestrial intelligence, has now been running in various forms for over 75 years. In that time, it has scanned billions of radio channels across thousands of star systems. It has expanded from Drake's single dish to a network of observatories spanning 6 continents. In 2015, the Russian billionaire Yuri Milner committed $100 million to fund Breakthrough Listen, the most comprehensive SETI program ever launched, using telescopes at Green Bank, Parkes in Australia, and the Meerkat Array in South Africa. The search has changed its language over the decades. Where Drake listened for a deliberate message, someone trying to reach us, modern astronomers increasingly hunt for technosignatures, the unintentional evidence any technological species leaves behind. Industrial pollutants in a planet's atmosphere, the glint of orbiting solar panels, the waste heat of a city. The logic is that a civilization might never choose to cool, but it cannot easily hide the simple thermodynamic residue of existing. We have begun, in other words, to look not for greetings, but for fingerprints. And the fingerprints, so far, are as absent as the greetings. The data collected is staggering. Petabytes of signal data, millions of hours of observation, algorithms designed to detect patterns too subtle for the human ear. And in all of that, across all those years, all those telescopes, all those channels, it has detected one signal it could not immediately explain. On August 15, 1977, Ohio State University's Big Ear radio telescope picked up a narrowband signal lasting 72 seconds. It was 30 times stronger than the background noise of space. It matched the theoretical profile of what a transmission from an intelligent source might look like: the right frequency, the right bandwidth, the right duration. The astronomer reviewing the printout that night, Jerry Eman, circled the anomaly in red pen and wrote a single word in the margin: wow. The signal came from somewhere in the direction of the constellation Sagittarius. It was never detected again. Not the following night, not the following year, not in the thousands of subsequent observations of the same patch of sky carried out over the next 4 decades. There have been attempts to explain it away. In 2017, a researcher proposed that a pair of passing comets, wrapped in clouds of hydrogen, had drifted through the telescope's field of view and produced the signal. The explanation made headlines. It was also, within months, dismantled by other astronomers. The comets were not in the right place, and clouds of hydrogen do not produce a signal that sharp, that narrow, that strong. The comet theory failed. The anomaly remained. It has never been explained, and it has never repeated. The wow signal was the search straining at the very edge of what it could hear. But in the decades since, the search itself has changed, and the instruments have taken a generational leap. Since 2022, the James Webb Space Telescope has been able to do something no instrument before it could. Read the atmosphere of a planet orbiting another star, parsing the starlight that filters through it for the chemical signatures of life. In 2023, it detected a molecule in the atmosphere of a distant world called K2-18b that, on Earth, is produced almost entirely by living organisms. The finding was tentative, hotly debated, and far from confirmed. It may yet dissolve under closer scrutiny, as so many signals before it have. But for the first time, we are no longer only listening for a message. We are sniffing the air of other worlds for the residue of life itself. The silence has forced scientists into uncomfortable territory. Over 75 years, dozens of explanations have been proposed for why the universe appears empty. Most of them fall into three broad categories, and each carries implications that are difficult to accept. The first, and most psychologically comfortable, is that we are simply rare, perhaps unique. This is called the rare Earth hypothesis. It was formalized in the year 2000 by the University of Washington astrobiologists Peter Ward and Donald Brownlee, and their paper has been cited over 3,000 times. The argument is that the emergence of complex, intelligent life requires an almost absurdly specific chain of conditions. Not just a habitable planet, but a cascade of improbable prerequisites that must occur in the right sequence, at the right time, in the right kind of galaxy. It begins with location. Not every part of a galaxy is equally hospitable. Too close to the galactic center, and radiation levels are lethal. Too far out, and the heavy elements needed for rocky planets, carbon, iron, silicon, oxygen, are too sparse. There is a narrow band, sometimes called the galactic habitable zone, where conditions permit the formation of worlds like ours. Our solar system sits inside it. Most stars do not. Then there is the star itself, the right kind, stable, long-lived, not too massive. The right orbital distance for its planet, narrow enough to sustain liquid water for billions of years. A large moon to stabilize the planet's axial tilt and prevent catastrophic climate. Oscillation. A gas giant further out, a Jupiter, to gravitationally sweep incoming asteroids from the inner system, reducing the frequency of extinction-level impacts to survivable intervals. Consider how many of those conditions our own world had to satisfy, in sequence, by accident. The collision, 4.5 billion years ago, that tore a chunk from the young Earth and formed a moon large enough to steady our axis. Without it, the planet would lurch through climate extremes no complex life could endure. The plate tectonics that recycle carbon and regulate temperature across geological time, a feature we have not confirmed on any other rocky world. The 2 billion year ordeal it took for oxygen to accumulate in the atmosphere, a transition so slow and so contingent that on most worlds it may simply never finish before the star burns out. Then there is the chemistry, the timing, and then the one transition that may be the rarest of all, the leap from single-celled to multicellular life. A paper published in the Proceedings of the National Academy of Sciences in 2018 estimated the probability of this transition occurring within a given planet's habitable window at less than 1 in 10 billion. If the rare Earth hypothesis is correct, then the silence is simply the sound of a universe where no one else made it this far. We are extraordinary, and we are alone. But it requires us to believe that a cosmos 12 billion years old, containing 2 trillion galaxies, each with hundreds of billions of stars, produced exactly one civilization capable of asking the question. That conclusion asks a great deal of us. There is a second possibility. It is darker. It is called the dark forest theory. The Chinese physicist and novelist Liu Cixin developed the idea most fully in his science fiction trilogy, The Three-Body Problem. But the underlying logic draws on serious academic work in game theory, evolutionary biology, and interstellar strategy. The argument begins with two axioms. First, survival is the primary need of every civilization. Second, civilizations continuously grow and expand, but the total matter in the universe does not. From these, a chain of logic follows. In a universe with finite resources and uncertain intentions, the safest assumption about any unknown intelligence you detect is that it could, eventually, constitute a threat to your survival. You cannot know its values. You cannot assess its military capability. You cannot know whether, given enough time, it would choose coexistence or annihilation. And here is the problem. Communication takes years, decades, centuries. By the time you learn enough about another civilization to determine whether it is peaceful, it may have advanced technologically beyond your ability to contain. The rational strategy, therefore, for every civilization, everywhere, is silence. The universe in this model is a dark forest at night. Every civilization is a hunter moving between the trees, quiet, watchful, never lighting a fire. Because in a dark forest, any signal you produce can be seen by anything in the darkness, and you do not know what is watching. If the dark forest is real, then humanity has already made a catastrophic error. Since the 1930s, Earth has been radiating electromagnetic signals into space, television broadcasts, military radar, commercial transmissions. That expanding sphere of noise now extends roughly 100 light-years in every direction. 100 light-years encompasses approximately 15,000 star systems. It is not large by galactic standards, but it is there. It is growing at the speed of light, and it cannot be recalled. In 1974, the Arecibo Observatory in Puerto Rico deliberately transmitted a message toward the globular star cluster Messier 13, a beam of radio energy carrying a coded description of our solar system, our DNA, and the form of a human body. It will arrive in roughly 25,000 years. We are not merely leaking, we are broadcasting. This is not a fringe anxiety. Stephen Hawking, who thought about these questions for most of his life, warned publicly and repeatedly against advertising our existence. He pointed to our own history. When a technologically advanced civilization on Earth encountered a weaker one, the outcome was rarely good for the weaker. A more capable intelligence, he argued, might regard us the way we regard insects. His advice was blunt. Listen. Do not transmit. And yet, a faction of scientists argues the opposite, that hiding is both futile and cowardly, that any civilization capable of harming us could already read the heat and chemistry of our planet regardless of our broadcasts, and that the only way to ever break the silence is for someone, eventually, to speak first. The debate has no resolution. It is, at bottom, a wager about the temperament of strangers we have never met and cannot imagine. And every year, we keep transmitting anyway. Not by decision, but by default. Whatever is out there, if anything is, has had time to notice. But there is a third answer. And it is the one that scientists, when they are being fully honest about what it implies, find the most difficult to sit with. It is called the Great Filter. The concept was first proposed by the economist Robin Hanson in a 1998 paper titled simply, "The Great Filter. Are we almost past it?" It begins with an observation that is hard to argue with. Something, somewhere, is preventing the emergence or long-term survival of detectable civilizations. Some step in the long chain from simple chemistry to spacefaring intelligence is either extraordinarily improbable or extraordinarily fatal. That step is the filter. The question that matters, the one Hansen framed and that no one has been able to answer, is whether the filter is behind us or ahead of us. If it is behind us, then we have already passed through the hardest step. The emergence of the first self-replicating cell, the leap to multicellularity, the development of neural complexity, the invention of language. We are survivors, standing on the far side of a barrier that most life in the universe never crosses. The silence is the sound of everyone else still trapped on the other side. If the filter is behind us, we are rare, and we are safe. But if the great filter is ahead of us, then it is something that civilizations like ours, intelligent, curious, technological, ambitious, routinely fail to survive. And we are walking toward it. It could be climate destabilization on a planetary scale. It could be engineered pathogens released, deliberately or accidentally, before containment protocols mature. It could be artificial intelligence that escapes the constraints of human alignment. It could be nuclear escalation beyond the threshold of recovery. It could be resource depletion so total that the civilization cannot rebuild after collapse. Or it could be something we have not yet imagined. Some capability that every civilization inevitably discovers, and that every civilization inevitably turns against itself. Each of these candidates has a disquieting feature in common. They are not external. No asteroid, no hostile fleet, no exploding star. Every version of the filter ahead of us is something a civilization does to itself, a consequence of the very intelligence that let it reach the threshold in the first place. The same curiosity that builds a radio telescope builds a bomb. The same ingenuity that decodes a genome can synthesize a plague. The filter in this reading is not a wall the universe puts in our path. It is a trap folded into the nature of intelligence itself. The silence in this reading is not the universe being empty. It is the universe being full of civilizations that almost made it. There is an unsettling corollary to this framework. If we were to discover microbial life on Mars, or in the subsurface oceans of Europa or Enceladus, it would not be entirely good news. It would mean that the emergence of life is not the hard step. The filter is not behind us at that stage. And if life arises easily, but the galaxy is still silent, then the filter must be somewhere further along the chain, somewhere we have not yet reached. The discovery of simple extraterrestrial life, paradoxically, would be evidence that something ahead of us is very, very dangerous. As Robin Hanson wrote, "The more we find that the early steps of life are common, the more we should worry about what comes later." dark forest, the great filter. These are the three answers that dominate the conversation, but they are not the only ones. And some of the alternatives are stranger, and in their own quiet way more unsettling than the silence they are trying to explain. Consider the possibility that we are not late to the party, but impossibly early. The universe is 13.8 billion years old, and to us that sounds ancient. But the smallest, longest-lived stars, the red dwarfs that make up 3/4 of all the stars in existence, will burn steadily for trillions of years. On a cosmic timescale, star formation has barely begun. By one estimate, fewer than 1 in 10 of all the planets that will ever exist have formed yet. If that is true, then the great age of life in the universe is not behind us and not around us. It is in the deep future, and we are among the very first to arrive. The silence would not mean we are alone forever. It would mean we are early, the first guests in an empty hall, mistaking the quiet for proof that no one else was ever invited. In 2016, 2 astronomers, Adam Frank and Woodruff Sullivan, tried to ask a more answerable version of Fermi's question. Not how many civilizations exist right now, which depends on that unknowable final term, but whether any technological civilization has ever existed anywhere in cosmic history. With the exoplanet data we now have, they could finally put a number on it. For humanity to be the only technological species the universe has ever produced, across 2 trillion galaxies and all of time, the odds of a habitable planet ever giving rise to one would have to be worse than 1 in 10 billion trillion. That is not impossible. But it means that to believe we are alone, you must believe in a number that small. Or perhaps the silence is deliberate, and ours is not the only side keeping it. The zoo hypothesis proposes that advanced civilizations know precisely where we are and have agreed, for reasons of their own, to leave us undisturbed. A developing intelligence, observed but not contacted, allowed to find its own way, the way a film crew watches a wild animal without ever stepping into the frame. Under this reading, the absence of evidence is the evidence. A galaxy that was genuinely empty would look noisy, full of expanding, careless, signal-leaking young civilizations like ours. A galaxy that is silent and watched would look exactly like the one we see. The unsettling part is not the thought that we are being observed. It is that, if it is true, the observers have already decided we are not yet worth speaking to. And there is a final family of answers that asks us to question the assumption underneath the entire paradox, that an advanced civilization would want to expand at all. We assume intelligence spreads outward across stars the way bacteria fill a dish. But a civilization that masters its own technology might turn inward instead, into virtual worlds, into pure computation, into spaces richer than anything the physical cosmos can offer, occupying less and less room as it grows more and more capable. Some have gone further. One hypothesis, proposed by researchers at Oxford, suggests advanced civilizations may simply be waiting, that computation is vastly more efficient in a colder universe, and that the patient strategy is to sleep, dormant, until the cosmos cools billions of years from now. A civilization following that logic would not be expanding, it would be resting in the dark, and it would look, to a young species scanning the sky, precisely like nothing at all. 1990, the Voyager 1 spacecraft, then nearly 6 billion kilometers from Earth, further from us than any human-made object had ever traveled, received a final instruction from NASA. The probe had been launched in 1977, carrying with it a golden phonograph record, a message from Earth to anyone who might find it. The record contained greetings in 55 languages, the sound of a heartbeat, a mother's kiss, the crash of surf, the songs of humpback whales, and 90 minutes of music ranging from Bach to Chuck Berry. It carried 115 images encoded in analog: a woman nursing an infant, a sunset, a diagram of human DNA, a photograph of a supermarket. It was the most ambitious message in a bottle ever constructed, and it was aimed at no one in particular. It was aimed at the silence. We have not only listened and broadcast, we have begun, tentatively, to reach. In 2016, a project called Breakthrough Starshot proposed sending a fleet of probes no larger than a postage stamp toward the nearest star system, Alpha Centauri, driven by a ground-based laser to a fifth of the speed of light, crossing in 20 years a gulf that would take Voyager 70,000. It has not been built. The engineering is at the edge of possible, but the intent is there. 4 light years away, and for the first time, not entirely beyond our reach. "13 years after launch, the astronomer Carl Sagan lobbied NASA to turn the probe's camera back toward the inner solar system for one last photograph before its imaging system was permanently powered down. There were objections. The image would serve no scientific purpose. Earth would be too small to resolve. The sun might damage the camera optics. NASA eventually agreed. What Voyager captured became one of the most studied images in the history of science. Earth appears as a fraction of a single pixel, a pale blue point of light, barely distinguishable from the sensor noise, suspended in a beam of scattered sunlight. It occupies less than 12/100ths of a pixel. Around it, in every direction, nothing but the void. Sagan spent the remaining years of his life writing and speaking about that image. He called it the pale blue dot, said it was the most important photograph ever taken, not for what it showed, but for what it put into perspective. Every war ever fought, every civilization ever built, every piece of music ever composed, every act of kindness and every act of cruelty, every birth and every death, everything that has ever happened in the entire history of our species, all of it contained on a mote of dust suspended in a sunbeam. And around it, in every direction, as far as any instrument has ever looked, silence. Here is what we know. We have searched for 75 years. We have listened across billions of radio frequencies. We have scanned the sky for laser pulses, for infrared anomalies, for megastructures that would betray the presence of a civilization large enough to harness the energy of its star. We have pointed the most powerful telescopes ever constructed at thousands of star systems and asked a single question: is anyone there? We found the wow signal, unrepeated and unexplained. We have found nothing else. Some scientists argue that we have barely begun to search. The astronomer Jill Tarter, who spent decades directing SETI research at the SETI Institute in Mountain View, California, once compared our search of the cosmos to scooping a single glass of water from the ocean and concluding that there are no fish. The electromagnetic spectrum is vast. The sky is enormous. Our instruments, for all their sensitivity, have surveyed only a sliver of what is out there. And there is a humility buried in the numbers that is easy to miss. Every search we have ever run assumes we would recognize a signal if we heard one, that an intelligence millions of years beyond us would reach out in a way a 20th century radio engineer could detect. We searched the waterhole because it made sense to us. We listened for radio because radio is what we had just invented. It is entirely possible that the galaxy is speaking constantly in a medium we have not yet discovered, and that our 75 years of silence is simply the silence of a species listening at the wrong door. Others argue that the silence itself is data, that if civilizations were common and long-lived, they would not all be silent, that the absence of evidence, accumulated across 75 years and billions of channels, is beginning to look less like an unanswered question and more like an answer we are not yet willing to accept. The Fermi Paradox has no answer. That is not a failure of science. It is science being honest about the boundary of what it currently knows. And perhaps that is the most remarkable thing about the paradox. It is not a question about aliens. It is a question about us, about how long civilizations last, about whether intelligence is a gift or a trap, about whether the technologies that allow a species to reach beyond its own atmosphere are the same technologies that eventually destroy it. Every proposed solution to the Fermi paradox is, in the end, a statement about what kind of universe we live in. Are we rare? Are we early? Are we being watched? Are we being avoided? Are we approaching something from which no civilization returns? What unsettles scientists most is that the same evidence fits all of them. A galaxy where we are the only ones who ever made it. A galaxy full of hunters keeping silent. A galaxy of civilizations that rose and destroyed themselves. A galaxy too young to have anyone else in it yet. A galaxy watching us and choosing not to speak. Every one of those universes produces the exact silence we observe. The data cannot tell them apart, and each of them asks something profoundly different of us: to feel precious, or afraid, or patient, or humble. The silence is a mirror. What we read into it says more about us than about the dark. We do not know, and the silence offers no guidance. What we do know is this: we are here. One planet, one star, one galaxy among 2 trillion. We have existed for a cosmological blink, 300,000 years as a species, barely a century of technology capable of reaching into the dark. And we are the only voice, so far, that the universe has heard from. Whether the filter is behind us or ahead of us, whether we are rare or early or simply improbably lucky, one thing follows from all of it. This moment, this fragile, specific, improbable window of existence may be harder to come by than we have ever allowed ourselves to believe. Every generation before ours lacked the technology to ask the question. Every generation after ours may lack the luxury of indifference to the answer. We are, perhaps, the first civilization in this galaxy to stand at the precise point where the question can be both asked and acted upon. Enrico Fermi finished his lunch that day in 1950. The conversation moved on to other things, other problems, other calculations. He could not have known that the question he asked in passing, 3 words spoken between the main course and dessert, would outlast him by decades and remain unanswered long after everything else he calculated had been confirmed, published, and taught in universities around the world. He died 4 years later. The question is still open. And out there, in the direction of Sagittarius, somewhere among the 40 billion potentially habitable worlds of this galaxy alone, the answer may already exist. It is either waiting for us to find it, or it has already decided not to be found.